Hello everyone, am I visible? Hello everyone, am I audible? Hello everyone, am I visible?
Yes, yes.
And also, audio is clear or not? My audio is clear or not? Okay, okay. Welcome everyone. This is a week two live interaction session of ground improvement, uh, which is conducted by Nptel team. I think we will wait few minutes to join others, and the session will be started soon. Please wait and be patient. I think it is the time to start the session. Hello everyone. This is the week two live interaction session of ground improvement, uh, which is conducted by Nptel, and this lecture plan are taught by Professor uh, Dilip Kumar Vaidya sir, and I am one of his TA to assist this course in this session. Uh, First of all, I introduce myself. My name is Rajat Bonik. I am from IITISM Dhanbad. I am a PhD research scholar and also a PMRF scholar, and getting chance to in uh, to uh, assist in course ground improvement course under Professor Dilip Vaidya sir in MPTL. In this session, uh, I think am I audible or not? Eh? Eh, Hello everyone, am I audible and visible also? Okay.
Audible.
In this session, we will try to cover the week two lectures, and then try to solve some problems in these lectures, and also try to solve previous year assignment problems, and then we will live interaction or discussion session to end this session. Okay, first of all, we revise in 10 to 15 minutes the previous week one lectures, and now I am sharing my screen. Let's start. Is this slide visible? Hello everyone, is this slide visible? Slide is visible or not?
Visible.
Yeah. Okay, let's
Yes,
start.
sir, visible.
Let's start with previous lectures by revision. Quickly go through these lectures, week one lectures. In week one, we learned about different type of civil engineering material, where soil also one of that. But in soil case, it is very dynamic and also very uh, dynamic and also uh, very not quality wise very not good, and it is not a factory made and also naturally available. So by this we cannot go with foundations or any other building in directly to the soil without inquiry the soil how it is or not. Then we learn how soil is formed, where it is, what cycle it is follow, how to form rock, how it is formed on that. That is from igneous and metamorphic sedimentary rock by degradation and heat and pressure. This soil is formed. Then we study the why the ground improvement is needed. Actually, in this we studied that if not suitable available ground or is available very rarely available or suitable ground is very rarely available or favorable ground condition is not available. That's why we go with ground improvement techniques. Then we go with different types of or learn different types of geomaterials like natural geomaterial, field geomaterial. In natural geomaterial, we learn soft clay, silt, organic soil, loose sand, expansive soil, loose. And we also studied the what are the different potential problems in this uh, in these different types of geomaterial. And also we studied the different types of field material. Actually, we ground improvement we mainly deal with the different type of field how to improve the field and how to construct in this field or not. And there are also different types of potential for in that, like compressibility, high compressibility, low strength, and high permeability, like that. And also we study the different type of geotechnical problem and what are the possible causes to that problem, like bearing capacity failure, total and differential settlement, ground heave instability, and what are the basic or fundamental theories based on which that failure occurs, and what are the possible causes also we are. Then there are also some other problems like liquefaction, erosion, and seepage also occurs, like that. And also we study the ground improvement method for transportation infrastructure. What are the different types of ground improvement technique apply in transportation, like aggregate column, refuse, waste material, electroosmosis, micropile, like that. Here so many ground improvement techniques in this table given. Then in module 1, lecture 2, we studied the classification of different types of ground improvement methods. Here, different types of scientists or authors give their different types of ground improvement techniques based on the different type of criteria. Like Mitchell gives the based on the construction and function criteria, six types of ground improvement techniques like in situ compaction, post pre-compaction, injection, like that. And also there are other few scientists like Hausman. It is given by process criteria. Then A et al. It is given also by function criteria, and Chu et al. It is given by soil type and inclusion, like that. And we also study our our own differentiation in ground improvement technique, like the shallow replacement method, where we learn the over excavation replacement method and what are the benefits and how it is applied, and in which type of soil it is applied and how much depth is needed and suitable applications, like that. Like in our excavation we go with up to 3 meter deep, like that. And then we study the shallow densification and what are the different types of like traditional compaction, high energy impact roller compaction, interdigital compaction, and what are the benefits like that there's like, and what are the suitability. Like traditional compaction use at a lift thickness up to zero point 0.3 meter, up to zero point 0.3 meter, and energy impact roller is up to 6 meter depth. We can improve the ground. Then we also learn about the deep densification. In deep densification, we learn about dynamic compaction and vibro compaction. Both are used widely in the field, and both are in heavy weight and heavy machineries are used in that, and also improve the ground in large extent like 15 to 5 to 15 meter up to sometimes 30 meters, like that. And also what type of material it is suitable, like dynamic compaction, it is suitable when the fine content is less than 15%, and fiber compression is suitable when the fine seals 15% seals or 20% clay are present less present. And also in deep densification, in module 1, lecture 3, we learn in deep densification other different types of deep densification like sand compaction column, stone columns. Like it is also improve the ground 5 to 15 meters or up to in some case up to 30 meters. And also we learn the different procedure how it is applied in the ground. Like sand compression, it is applied by driving a caisson and fill the sand. And so stone column is also the same, but in stone column you apply jet water or air also to displace the problematic soil and fill it is by stone or good geomaterial, which is also can and which is also can apply in accelerate the consolidation process and reduce the water in the under the ground, and also settlement take place and improve the ground. And it is a procedure, and also we studied the procedure how stone column is formed. There is one type of procedure, the dry bottom feed method, where we apply directly at the bottom stone and vibrate it and compact the soil and and upward, go with upward direction and form the stone column. Gradually upward direction and form the stone column. And then we've studied the deep replacement. Previously, we studied the deep desification. They are two different in meaning. In previous case, we apply only densify matter, no removal of the, we apply some material, good material, and no removal of the material. In this case, replacement method, we remove the problematic soil by steel casing or other driving techniques and apply the good material to resist the column. Here we resist the soil or strengthen the soil. Here we apply two types of techniques. One is rammed aggregate column, another one is geosynthetic encased column. In ranked aggregate column, it is pre-drilled or backfilled with the aggregate or densified by rim. And in also steel driving column, geosynthetic encased column, we driven the steel casing and apply the geo material or geosynthetic casing and fill it. In both the case, we benefits are the bearing. We increase the bearing capacity and reduce the settlement liquefaction like that. Also, it is applied for up to 5 to improve the ground up to 5 to 10 meter. Moving forward, we have learned about the different drainage technique. Drainage is also one of the ground improvement techniques. It can use here in two types. By two types, one is field drains, another one is drainage geosynthetic. Both are reducing the or expelling the water from the ground and lowering the ground water table, which is increasing the effective stress and also increasing corresponding increases the bearing capacity and shear strength also. And it is commonly applied. These two methods is commonly applied in roads, retaining walls, and slopes like that. And then we also learn about the dewatering technique, different type of dewatering technique, that is open pumping and well system. In open pumping, it is up to shallow area or small area. It is limited in shallow area and small depth also. In well, it is quite large area cover to improve the ground. And both the case we remove the water from the construction site to ease the construction, increase the stability. Then we learn about the consolidation technique. In consolidation, you use the field preloading and vacuum preloading. In field preloading, we apply some temporary structures and we apply some sensory structure in. Then by this structure, we increase the excess pore water pressure, and by excess pore water pressure, it is by voids or pore phase, it is expelled out from the ground, and the ground is settled down and thus stabilized. Then after the ground is stabilized, no further settlements occur. And it is also accelerated by sand drains or stone column to increase the drainage path, and by this we accelerated the process very quickly. And same wise, vacuum preloading is also applied by vacuum pressure. The same procedure is quite similar, but in case field preloading we apply temporary structures, but in vacuum preloading we apply vacuum pressure also. Both are suitable and both are same objectives. Both are same objectives like that. Both are reduce the settlement of the foundation and increase the strength and of the soil. Here is one of the some schematics picture of that. And we also learn about the shallow chemical stabilization. In shallow chemical stabilization, we in techniques are chemical stabilization of subgrade and base. Where we apply the lime, cement, and fly ash like that, and we injected the ground and stabilize. And when the slime and cement react with water and strong and stone like material is formed and grounding, cementous material form and ground is increase stable and increase the strength, stiffness, also reduce the ground heat like that. But it is up to a limited thickness or limited depth up to 0.3 meter only. But we for deep we can use deep chemical stabilization technique, which is nothing but grouting techniques and deep mixing technique. Both in both the case, we apply or injected the grout or chemicals in the ground by some machines like probes like that, and apply to take apply sometimes or we take that time to react the with soil and harden the soil mud. Both the cases, we increase the strength and permeability, and we reduce the ground heat we both the case we increase the strength and reduce the permeability and also reduce the ground heat. And then we studied in lecture 4 module 1 the field reinforcement. It is in field reinforcement we apply two types of techniques. One is geosynthetic reinforced slope and another one is for reinforced slope and another one is geosynthetic reinforced embankment. Both are similar objectives like increase the stabilities and increase the bearing capacity, and also suitable. Both are also suitable for low plastic field and embankment slope and like that. In another types of field reinforcement are the mechanically stabilized earth wall and geosynthetic reinforced road. In both mechanically stabilized artwork, we learn that we place the geosynthetic or metallic reinforcement in the wall at a different elevation during the field replacement and provide the tensile resistance to the soil. We know that soil is good in compression but weak in tension and shear. In this mechanically stabilized earth wall, we increase the tensile resistance of the soil, which can resist the soil and also good in good extent and also take the tensile resistance from the structure. Both are one is mechanically stabilized suitable for plastic soil, but in geosynthetic reinforced root is technique suitable for only granular soil. Uh, and then we studied the in situ reinforcement. And it is nothing but soil nailings or micropiles we apply in the ground. Which in the both the case we injected the small soil bars in the ground and grouted it, surrounding it, grouted. Like that we so in these techniques we also increase the tensile resistance of the soil, uh, the tensile resistance or strength of the soil, and increase the ground stability like that. And moving ahead, here we have showing one soil nailing picture where it is in previous the embankment is the dashes line and we reduce by applying the soil nailing technique. Here we injected the soil bar in the slope and grouted it and stabilize the slope, which can also take the tensile strength from the slope. Then we also learned the different types of thermal and biological treatment. One of them is ground freezing, and other one is biological treatment. In ground freezing, we reduce the temperature of the soil and below the freezing point, and if there is any moisture is present in the soil, it is hardened up and ground is strengthened in some extent, increase the strength and reduce the water flow and ground movement. But this technique is suitable for a temporary work potential during the excavation, like that, and also suitable for saturated clay and sand. In biological treatment, we utilize a vegetation technique and root technique to increase the shear strength of the soil. We vegetate or some grass in grass applied to the ground and by grass roots that is that is increase roots cover the whole soil and reduce the erosion of the during the rainy season like that, and increase the shear strength of the soil. Then we learn about the selection method. What for what type of what construction, what type of ground improvement technique used. That if the soil is good, no ground improvement technique is required. Only shallow foundation is suitable. If it's not good, it is the in little bit in low strength or problematic, it is we can go for replacement with that problematic soil. If further, we can go for consolidation technique, compaction technique. If not yet well uh, suitable, then we further go for composite ground improvement technique like sand column, stone column, like that. If also not suitable for the construction, go for the deep different types of deep foundation like pipe foundation, well foundation. Here also we can see the how the slope can fill or cut slope of the fill and cut can reduce by different type of ground improvement technique like reinforced earth cut and fill earth walls or by reinforced cut and fill slope like that. Then we also studied the different types of ground improvement method and factors. What are the factors? It is uh, occur. What are the factors? It depends on like structural, geotechnical, environment, and also you see the what type of soil and what type of soil and what type of technique is suitable. It is based on the particle size distribution only. That means if a particle size is point 1 to 10, we apply suitable. It is suitable shallow compaction, chemical gauss like that. And there are different types of also technique which is suitable for other types of soil particle. Then we can see the flow chart, one of the flow chart where we see the how the we start our construction, what are the different steps, and what for what and what is applied or what is not applied, like that. And if it is problematic, what type of downstream technique we go with or not. Then in lecture 5, we see the one of the previously discussed technique, one of the previously discussed technique, which is excavation replacement technique, where we learn the how much depth it excavated the problematic soil and how much size or width we replace the soil. Here it is shown that the if it is problematic soil, the depth of the width of the foundation B, the height of the problematic soil replaced is B2 sorry 0.5 to 1.5 BF. That BF means width of the foundation below the foundation level, and also width of the excavation or replacement is B to 3B sometimes. It is depend on the different types of soil. And also we go learn about the what are the different application it is, what up to what depth it is suitable or not, like that. And also we uh, see the why how much it is used and what are the benefits in these techniques, and what are the also what are the advantages and what are the disadvantages of these techniques. And also we learn about the principle like which soil and how it is used, and what are the techniques and how it is suited for the uncontrolled field and so on. And also we learn about the different failure modes for excavation and replacement technique. One of is general shear failure, another one is punching failure. Both are in within replaced zone. Another one is distributed failure through the replaced zone. Another one is punching failure into the underlying weak soil of the replaced zone. And also see how we see the uh, bearing capacity formula for general shear failure, and also learn the different shape factor and depth factor of this formula, bearing capacity factor, what are the formulas like that. Now we start week 2 lecture plan, which is conducted by the sir, and I am just discussing one by one of the slide. We start with week 2, lecture module, week 2, lecture 1. We start with one of the another type of Garnier technique, which is nothing but shallow densification. We start with this principle. We know that shallow densification, by name, it is know that the densify the soil up to a certain depth, not by in great extent. We have apply densification technique up to a certain depth, like zero point 0.3 meter or in zero point 0.3 meter or zero point 0.5 meter of the from the ground surface. In the shallow densification is nothing but the compaction, which is also we learn in soil mechanics. In shallow densification, we apply the energy to compress the soil or soil particle to come closer, or expel the air void or void spaces, or we simply call the reduction of the void ratio, but it is quite similar to the consolidation technique. Both are the same purpose. We reduce the volume of the soil or compress the soil particle to come closer. But in procedure wise, these techniques are different. In consolidation, we actually reduction the void ratio by applying some load or constant load in longer period of time. Due to this constant load or temporary load, excess pore pressure is generated over the period of time, and this excess pore pressure is expelled out by the pore phase, and because water is incompressible in nature, it is tied to always try to flow, or is pressurized, if always try to flow where it is find the gaps or pores like that. Then after expel the excess pore water pressure by applying some temporary loads, water particles clump closer, ground is settled, and ground is stabilized for further construction. No further settlement is occur after consolidation. But in case of compaction, or what is called the shallow densification, we apply the mechanical energy or some energy to apply on the ground and expel the uh, air from the ground, or air from the soil, or air voids from the soil. But it is instantaneous process. But consolidation is slow process. It is takes consolidation takes it few months, sometimes few months, or sometimes a few weeks also. But in compaction, it is instantaneous. We apply load, expel the pore water pressure, sorry, except for voids, air voids, it's like that. And there is some simple difference here also. In saturation, we require saturation of soil in essential soil in consolidation, but we need not require the saturation, ground saturation in compaction technique. Moving ahead, we discuss now the principle of the shallow compaction. Here in principle, we actually uh, see the three uh, effects. In shallow densification, we mainly use for three reduce or improve the three effects. One is here strength, another one is settlement, and another one is permeability. In compaction, increase the in the principle is in compaction we apply the mechanical energy. By this mechanical energy, the soil particle come closer and expel the air or pores or air voids like that. But, and also increase by this procedure we increase the soil density, increase the shear strength, and decrease the future settlement of the soil, and decrease the permeability of the soil. In this principle, we mainly discuss that these three effects are beneficial for the any type of construction, for any type of construction which is related to the earth structure, namely highway, airfield, other dam, etc. also in principle we know that if we it is common that if we apply the getter energy we will get greater benefits also. Like like that we apply greater mechanical force or mechanical energy. The soil this energy is by this energy soil is more number of soil particles is come closer and more air voids or is expel out like that. And in this technique is ancient technique. It is one of the great technique. And readily available and cheap technique to improve the ground, mainly for earth structure like highways, railway, and earthen dams like that. And it is also very cheap. Everywhere where the finishing work is done by this technique only. After we improving, like if we apply deep densification there, after finishing the soil layer or top layer, we apply the shallow densification to smoothening the ground. And then we go here see that different types of machines or machineries used to this shallow densification. Here we see the three pictures of that. One is, here is sorry, sorry, we start again. Here we three different types of geomaterials are used. Sorry, different types of machinery used for improve the ground by shallow densification. One is compaction technique. Another one is uh, one is smooth roller. Another one is second picture is pneumatic rollers. Third one is vibratory plates. In smooth rollers, uh, um, rollers, plates, repeated, apply static pressure, kneading action, vibration on the ground surface, or densify the geometry. So, in smooth wheel roller, we apply the mechanical energy to smoothing the ground surface. In smoothing the ground surface or finishing purpose of the top layer of the surface. In pneumatic pressure, it is actually has a high inflated tires, pneumatic tires equipment. It is a high inflated tire which is improve the ground. It is actually the pressure is more than the smooth wheel roller, and it is improve the ground more than the smooth wheel roller. Then the third picture is vibratory plates. Actually, vibration is help in overcome the resistance between the soil particle, and it is easier to it is easier to overcome the resistance of the soil particle, and soil particle will come closer with minimal mechanical energy. So vibrational plate is used to for that purpose only, and it is only used where these places inaccessible places. That means where the smooth roller or pneumatic or rubber tire roller are not or accessible or not go, like edge of the slopes, at the edge of the slope or backfill of the earth jam where we applied the vibratory plates. Now, the shallow densification methods, we come to a smooth roller. Actually, rollers are large and heavier than the compactors, and therefore they are commonly and efficiently used for large area compaction. That means roller in area wise, cross section area wise, a plan the roller arc is cover the more number of or large number of area. But in case of plate vibratory plate compactor, it is actually used for small area only to corner or edge, improve the corner or edge only. It is not possible to in big size. So it is for that purpose roller is more suitable to for larger area compaction. And it also in So in second point, it is stated that in constant areas or unsuitable edges, roller are not suitable because if we apply the pressure in unsuitable or unsuitable edges or corners, the corner may be break or shell failure may be occur because at that corner or edges the load distribution area is very less, so it may be fail after where it may be um, he- maybe maybe failure the soil by sharing or like that. Here we use only uh, plate compactor only. The application is that conventional compaction has been used for earthworks such as road, embankment, dams, slope, and parking lots and sports field. Sports field in the sense it is like football ground or the cricket pitch also. Here we have different types of soil geo material, and for that material we apply different type of moisture content and then apply the smooth wheel roller and or vibratory compactor or plate compactors to improve the ground or flatten the ground. It is mostly used roads and embankment only to improve the ground. It is very widely used, cheap, and mostly popular for this purpose only. Then we coming moving forward. There are few advantages and different limitation also for shallow densification. The advantages are the this we are already touched that or told that this equipment is readily available in the market and it is widely well established ground improvement method also, and anyone can who anyone or can learn or this equipment very easily, and in history also long history also it is very quite popular, so extension. So this technique is for this purpose only. This technique is very construction equipment is very good, but here it is some limitation. Because in shallow densification we improve the ground up to sometimes up to 3 meters up to 0.5 meter. It is depend upon different types of shallow densification techniques. So it is not quite good for further improvement of the ground. That is, if we we need to improve the ground above the 6 meter or like 15 meters. So that this shallow densification technique is not popular. That means the depth is improvement is limited and mainly used to field work. That means we like recycle field, uncontrolled field, dredge field, like that. This technique is used, and also not suitable for into geomaterial like soft soil. We learn about soft soil, clay, silt, like that, and it is also to apply this technique we also maintain the optimum moisture content all the time to increase to get the maximum benefits. So it is sometimes not possible to get in ground to get the optimum moisture content. So it is challenging to achieve, and also it is also challenging to achieve the uniform compaction of the geomaterial in a large area. Like sometimes when we apply the this shallow smooth hull roller or pneumatic or rubber roller, some area is go with the four passes, area go with the five passes. It is not understand what area is go with how much passes. It is quite difficult to judge or quite difficult to understand note down the number of passes for the large area. So for that, if for that the improvement technique also not uniformly uniformly distributed over the large area. So this technique is not good for that. So now we come to know how the shallow densification technique is applied in the ground. For first, we need to know the maximum dye density of for that soil in laboratory. How we can find that? We can find that by simple formula, which is also which is we learn in soil mechanics, basic soil mechanics in three-phase diagram, that gamma d, that is dry density, is equal to the gamma by 1 plus W omega, where it is gamma is bulk density and omega is water content. By this simple formula, we can find out the maximum dry density of that soil, and we need to know every time that dry density after the application of shallow densification, and we also whether it is achieve our goal or whether it is achieve our targeted densification or not. In most cases, actually, in most cases, we dry soil can be best compacted if the certain amount of water is added. In this shallow densification, which is different from consolidation, in consolidation we apply completely saturated to the ground. But in shallow densification compaction, which is also called compaction, we need not go or need to saturate the ground, but we need some amount of water. Why? Actually, we water is applicable as a lubricant. If water is applied in some amount, the particle to particle friction is reduced, the particle resistance is reduced, then particle easily come closer and a good pack to and come very close and reduce the volume and expel the air voids and soil like that. But if water we apply water too much water, then it is it is not is good for our field densification, because water the too much water can also occupy the void space of the soil. Uh, that is, if we apply too much water, the water is film water film is created around the every soil particles, and particle size is going to size effective particle size is big, and that by that the volume is increased. So by volume increase, we know that density is weight by volume. If volume is increased, automatically density is reduced. So if too much water also we add, the density of in situ density, soil density also reduces. Thus, for a given compactive effort means the mechanical force which we apply in that field. So, thus, for a given competitive effort, there is a particle moisture content at which the dry unit is greatest and compaction is for best. That means when we apply some water content, which is best for that soil, and we get the maximum dye density, is for which that water quantity is suitable for our construction, and it is nothing but called the optimum moisture content. And for every construction or every soil, there is a what optimum moisture content for what we get always a maximum dye density, which is called sometimes called MMD, MDD, sorry, MDD, and optimum moisture content is called OMC, and we get the OMCT for a particular compactive effort. That means particular mechanical energy. Moving ahead, here we show that here we see that one compaction curve. It is actually it is in y-axis it is dry unit weight, and in x-axis it is moisture content. So actually we by here you see that gamma d is equal to gamma bulk by 1 plus omega. So by this formula we created that type of curve. How it is created for, for initial stage, we in the initial stage we find out the initial moisture content, and we also find the maximum dry density, and we apply and plot it in this way that in y-axis we plotted dry density, and in x-axis we plotted the moisture content. We plot is say it is plotted 1 for first case is to 1. In second case we increase the water content by 2%, 3%, and we also again calculated the moisture content of that soil, of that type of soil, and also corresponding dry unit density, and we get the second point. Like that we get the third point, increasing the water content, and fourth point and fifth point. After plotting all these points, we get that like a best fitted curve like that, where we see that one point where we get the maximum dry density, that maximum density of the soil, and corresponding that we find out the moisture content, which is nothing but called the optimum moisture content. So like that, this curve is plotted, and we get the always whenever we plot or try to uh, different tests like standard Proctor test or heavy modified Proctor test, which is already in studied in the soil mechanics. We always like similar type of curve, like that type of same. First we increasing, then at some point it is maximum, and then after it is reducing. Always we get that similar type of curve for same type, different type of soil, and it is actually we cannot completely reduce the voids or air voids in that soil. It is not possible practically by shallow compaction. If we apply or theoretically apply the formula that we reduce or completely reduce or expel the air voids, then the curve is always parallel or like that, always like this, parallel to the lower side of the moisture content. Always we get the like that similar moving upward to downward. It is nothing but called zero air void line. It is always constant for a particular type of soil. It is not depend upon the compactive energy, not dependent upon the moisture content, uh, like that. It is always get similar type of curve for a particular soil. So it is only theoretically only this type of curve is possible, and it is always not intersecting in the main curve of the of our density curve. It is always there is some gap, because we cannot expel the complete airs from the soil. It is only theoretically it is only possible, not practically it is possible. So there is some gap always. So now moving forward, we can see the shallow densification curve for different type of compactive effort. That means if we apply low compactive effort, we get the lower side of compaction curve. If we apply higher compactive effort or energy, we get the higher maximum density or higher side of compaction curve. We can see that here it is four type of plot graph is plotted, 1, 2, 3, 4. In we apply first we apply the 20, up to 20 blows, that is low in the sense it is low compactive energy, so only 20 blows is applied. We find plotted the similar type of exercise like standard Proctor test or modified Proctor test. We plot the graph and get the optimum moisture content and dry density. And in the second stage or second plot, we increase same soil is conducted, but we increase the blows, number of blows. It is nothing but the increase the competitive effort or the mechanical energy. Then we get that the higher maximum die density than the lower side, and also decrease the our optimum moisture content. Like that, if we further increase our compactive effort or compactive mechanical energy, we get the higher maximum dry density and also lesser optimum moisture content. From this, we concluded that if we, for similar type of soil, if we apply lower energy, so we get the lower density, lower maximum density, and also get the higher optimum moisture content. But we increasing the compactive effort or mechanical energy, we get the higher density, and corresponding we also get the lesser optimum moisture content of the soil. So like that, if we plot it, that we see that curve is increasing, going upward and also shifted left side, that is shifted towards the dry unit line. So we see that we, if we, our compactive energy increasing, dry density also increasing, and corresponding moisture content, optimum moisture content is also reducing for the particular soil. And we also see that for a particular, if again previously told that for a particular soil, always the zero air void line always constant. We can see that for high energy compactive energy, low compactive energy, that means 20 blows per layer, 25 blows per layer, 50 blows, 30 blows per layer. So for similar type of, or always the same plot is plotted for zero air void line. It is not depend on the compactive effort or mechanical energy. So always we get the similar type of line for a particular soil. It is called for zero air void line. That means theoretically we reduces the completely zero the air voids. So we get similar type of curve, which is going upward to downward when the moisture content is increasing. So now we take few minutes breaks, like 5 to 6 minute break, and after that we can again start our lecture, and don't skip our live session. Further we continuing the session and completing the few problems. And now we can take few 5 minutes break. We will join 7:05, and don't leave this session. Thank you. आज कैसा था? Welcome back, everyone. Am I audible or visible?
Yes, audible.
Okay. Now we end our session with coming lectures. Uh, Now we going moving forward. We see that cellular densification for different type of geomaterial. What are the effects for cellular densification curve for different type of geomaterial? Okay. So here we can see the seventh plot for compaction curve, which is density, density versus water content. Here to see that at the top level, curve one, it is for well graded coarse to fine sand, and for at the bottom it is for seven. It is for sandy seal. Here we see that for well graded, well get the maximum dry density is achieved for oil graded soil. The maximum dry density is maximum for any other type of geometry. Okay, and it is also required to achieve that maximum dry density for a lower water content. But in case of we see that in case of silty soil, which is highly compressible or highly compressible in nature, it is we see that the compaction curve or maximum dry density is like very low, less than a for any other type of geometry, and also it achieve that type of maximum dry density we required also maximum for maximum water optimum moisture content or water content also. And all this graph we get for different type of geometry when similar type of compactive effort, that is similar type of or same type of or same mechanical energy we used. Okay, and that means for that for we getting for that type of different types of geometry, we like for 20 blows, that also 20 blows, this also for 20 blows, like that. That means similar type of where we constant the compactive effort and get the different type of compression curve. And we see that for different type of compression curve, well graded soil we get the good result, because in well graded sand the variation of soil from coarse to fine soil. In coarse soil, the voids between the coarse soil is filled with the fine soil. So that the air voids is replaced by the fine sand, and soil is the oil compacted and come closer very easily, and we get the maximum density or density to any other type of soil. Moving forward, that is in lecture 2 or module 2, we see that one type of three types of curves of optimum moisture content, compaction curve. This is the compaction curve which is we define for effective for water content for effective compaction. But what are the range of the water content for we get the optimum maximum dry density in field condition. So we see that we also know that for if we increase the competitive effort or energy, we get always the higher side the compaction curve, and also moving the left side of the curve graph. And if we choose that in field, if we choose that our targeted compaction is 20 and like 20 kilonewton per meter cube, that means we achieved the our dry density, maximum dry density up to 20. And say this point is we say this 20. Here we can, if we see in the graph, mark it is at 20. That means this point is we know that 20 kilonewton per meter cube. We achieve up to that time much maximum redundancy. And we trial and error. We apply three types of energy. One is moderated, another one is high energy, and another one is low energy. And if we a, draw a horizontal line like that, that we see that the the horizontal line is cross the 2 points in the that curve. One is lower side, another one is higher side. That is, one is drier side. That means another one is wet side. So wet side of the compaction curve. So we can say that if the high energy we apply, always our the range of the water content always, if we apply high competitive energy in this graph, we see that the range of the water content is also high. That means from W1 to W set or W2. If that much of water range or water content we can available, which means if in soil condition, if we the water content is in this range, we can easily achieve our goal. But in case of moderated, the range is usually reducing and further reduces, or sometimes the graph is also not crosses when the energy also further reduces a low energy. So in low energy, the range is very less, or sometimes it is negligible. So from this graph, we can easily identify the range of water or water content which is maintained in the field to achieve our targeted dry density. Then moving ahead, here we see the prediction of the optimum moisture content. If we apply prediction optimum moisture content and maximum dry density, you see that we by standard Proctor test and modified Proctor test or other some means we can previously apply. Say we can for same type of soil we can plot it these two types of graph. One is upper side, another one is lower side. We can see that this graph maintain the parallelism. That means the lower side also parallel to the lower side of the high energy compactive graph is parallel also the lower side of the low energy compaction graph, and also the higher side of the low high energy compaction graph also parallel to the high energy lower energy of the higher side of the lower energy compression curve. By this graph or previously developed compression curve, and also by the zero assumed or theoretically achieved a zero airborne line, we can predict our compression curve for a particular point. Like that, if we go with soil, field and test it at the maximum, find out the maximum density of the soil and corresponding water content, we can easily predict by this other previously developed compaction curve. One of is higher side, higher energy, another is lower side, and by this parallelly drawn or predict the compaction optimum compaction curve. Like that, you can easily find out. No need to further find out the other points for that type of soil for another compaction energy. Okay, moving forward, here you can see uh, one of the graph for applied energy versus maximum direct density. Here it is one applied maximum direct density in regular scale, and applied energy or compactive energy is in log scale or semi-log scale. We can see that when the energy is increased, the maximum direct density on also increase. That means in standard Proctor test, we get the maximum direct density up to that mark, and modified Proctor test, we get that much. The line is always increased. That means in standard Proctor test, maximum direct density is always less than the modified Proctor test maximum direct density. And in between any field, if the energy level is in between, we can easily find out that. So by this curve, we easily see that the is linearly varying when the maximum dry density is linearly varying with the compaction energy. That means if the energy is increased, maximum dry density also increase for that particular soil. Remember, the graphs are always for a particular soil. If the soil is material is changed, the graph also change. Okay. So moving forward, we can further see that there are different type of influential factor which is dependent or govern the relative compaction in that field. What is relative compaction? Relative compaction means the how much the compaction is achieved in the field with respect to the achieve maximum density in the laboratory. That means in formula by formula, if we apply by applying by formula, the relative compaction is equal to the relative compaction RC is equal to in situ dye density by maximum dye density in situ density at field by maximum dye density at laboratory into 100%. That means the how much compacted the ground with respect to the maximum dye density of laboratory testing. That means laboratory testing means standard Proctor test or modified Proctor test. This relative compaction is very important for ground improvement technique in the field or shallow compaction in the field. It is depend on the different types of soil. We can see that when the we material changes the compaction curve. That means for oil compaction, oil graded soil, the compaction curve is higher side, and in case of silty sand or silt, the compaction curve is lower side. That means the relative compaction also depend on the different types of geometry. Also, it is depend on the moisture content. When the moisture content is lower side, the maximum dry density is less than the maximum dry density, and also when the optimum moisture content. Also, when the content is greater than the optimum moisture content, also it is maximum density is less than the maximum dry density. So it is also depend upon the moisture content of the soil. Okay. Then we coming forward, we see the compaction method also. That means what type of compaction method we use. It is also depend on the influencing the relative constant. That is, we use either standard Proctor test or we use the modified Proctor test. We know that in standard Proctor test, sorry, in modified Proctor test, we get the better result than the standard Proctor test. So also the methodology or method also depending the relative compaction in the ground. Then compaction effort, including the applied energy, also depend. That means if we apply higher energy, we get the higher or maximum dye density. And also it is also depend on the leaf thickness and number of passes. That means how much, up to how much or how depth improve the ground. Up to hot depth, we improve the ground. It also depend. If we small, if we the lift thickness is small, the low compaction compactive effort is applied. If lift thickness is high, a high compaction energy is applied. Also, if the number of persons will increase, the maximum density also increase. If the number of persons is less than less, the maximum density is also less. And also, it is dependent on the relative stiffness of the ground, layer stiffness. That means if the upper layer is more stiffer than the lower layer, then the ground the lower layer is not compacted because the energy is resisted by the upper layer because of its stiffness. Because upper layer has higher stiffness than lower layer, so the relative stiffness also depend on the define the relative compaction of the ground in the field. Then moving ahead, we see the we study the density versus depth curve. That means the density. If we apply the shallow densification technique or method or compaction technique, it is vary with also a depth. That means in the upper side or at the closer to the ground, the density for same compaction energy, the density is in so the density is less than the less, and if we further moving below the ground, the density further increase, and then again further we moving down, the density again less. That means there is also an optimum point. That means that middle point where we get the higher or maximum dry, higher relative density, or maximum dry density. So for one layer or one thickness or one lift, we cannot improve or target our goals. That means if we targeted that our relative compaction is 80%, relative compaction is 80%. That means like that only that up to only that type of layer. That means 0.3 to 0.6 meter only achieve our goal, not the up to 0 to zero point 0.3 meter, not zero point 0.6 to further 0.12 meter. So for this case, we divide the lift thickness or divide the layer. That means from in a number of layers. That means from zero point 0.8 to 1.8 to 1.2, we applied one type compaction energy. Then zero point 0.6 to 1.2, we applied and again compaction energy. Comfort, then mechanical compaction, and again from 0 to zero point 0.6, we apply again the compaction energy or shallow densification. By this, we can achieve our goal. That means if we draw the line for that, that means maximum layer can maximum layer depth can within this relative density. So we can increase by R, we increase by a number of layer, we increase it at a greater depth by shallow compaction also to achieve the maximum dye density. So again, moving forward, here it is the range of define the range of water content required for different in the field. What type of range should be maintained in water content is maintained in the field. So in this, we discuss that in here we see that normal one type of compaction curve, and it is a zero airborne line. Here it is a compaction curve for some degree of saturation. So in this curve, we see that the left side of the this point is maximum dry density. This point is optimum moisture content. So the left side of the optimum moisture content we call it is dry side, and the right side of the optimum moisture content we call it a wet side. And the left side is suitable for the shear strength, and right side is suitable for the permeability. That means if we increase, if we need the increase the strength of the soil, we need to water content should be limited to the dry side of the optimum moisture content, so we can get the maximum shear strength. But if we need to overcome permeability or impermeable layer, we need to improve our soil over the greater than the optimum moisture content or white side of the optimum moisture content. So moving forward, in this table, we see that the range of the water coin should be maintained for achieve the relative compaction in the field. And this range is defined from the optimum moisture content for that particular soil or field. For the roads, we can say if we have achieved the 90 to 100 to 5% maximum dry density, maximum dry density with respect to the laboratory in the field, that means if our relative compaction is 90 to 105, we have to maintain the optimum moisture content from -2 to +2. That means the range, if like that, if it is 16%, we get the optimum moisture content. Then the range should be 14% to 18%, like that. Further, in road, if the depth of the road is greater than 0.5 meter, the maximum dry density should be maintained 90% to relative compaction or maximum dry density with respect to the laboratory should be maintained 90% to 95%. And also the range should be optimum moisture content range should be -2 to +2. But always the range should not be equal. Sometimes it is unequal. It depends on the benefits or depends of the applicability of our techniques. Like if for dam, the maximum the moisture content should be always in the wet side of the optimum moisture content, because we need in dam we actually overcome the or restrict the water flow or water. For that, we need to build the impermeable layer. We know that the best for impermeable layer is built when or constructed when the moisture content is in dry wet side of the optimum moisture content. So we see that the range should be -1 to +3. That means the optimum moisture content, weight of the optimum moisture content is greater than the dry side. So like that, the larger dam also we have the relative compaction is 95%, embankment for relative compaction is 95%, and so and so. Moving forward, we can also see that for different type of geomaterial, what type of uh, machines or what type of technique we use for shallow densification. Like for rock fill, when we improve the rock fill, first choice will be vibratory roller, because with vibration, because due to vibration, the particle resistance is reduced and particle get closer to each other. So first oil always should be vibratory roller. But if not available, vibratory roller if not available, then the rubber tire roller is also a good option. Like plastic soil and low plastic soil, like clay, high plasticity clay, high plasticity seal, or low plasticity clay or low plasticity seal. Sheep food roller should be great option, because in sheep food roller, in sheep food roller there is in like sheep food, there is some protrusion or some needle type is moving coming up from the surface, and it is a kneading effect. By kneading effect, it has a kneading effect. By this kneading effect, we can easily, and by the self weight of the roller also, the densify the soil, and it is very good for low plastic soil and high plastic soil. That means the silt and clay. And this type of soil, uh, this seafood lure is working on the principle of kneading effect. Remember kneading effect and self weight of the roller. And if seafood roller is not available, we can also go with the rubber tire roller, which is where we can go and apply high energy than the smooth oil roller. Then plastic sand and gravels. Plastic sand and gravel, we can use vibratory roller or pneumatic roller. Pneumatic roller is nothing but the rubber tire roller also. Also can we use the pet food roller. In silty sand and gravel, we can use vibratory roller, because sand and gravel is also a cohesionless soil. A cohesionless soil is best compacted by the vibration. If not available, we can go with the rubber tire roller or pet food roller. And clean sand, we can also use vibratory roller. And in clean gravel, we can also use vibratory roller. It is a fast choice. Moving ahead, there is we now differentiate different type of compaction machinery, like sheepfoot roller, rubber tire roller, smooth roller, depending their applicability and leaf thickness and number of passes. Like sheepfoot roller is applicable for fine grain fields or coarse grain fields with more than 20% fine, and it is a leaf thickness or improved the ground up to 0.15 meter or 150 mm, and it is required for to 6 number of passes for fine grain soil, 6 to 8 number of passes for coarse grain soil. Then we can go, we know the we then there is come rubber tire roller. In rubber tire roller is applied when the coarse grain fills with 5 to 4% soil. That means when the clean coarse grain soil 5 to 4% is available in the ground, we can go with the rubber tire roller. And the leaf thickness is more than the seafood roller because the compaction energy is more than the seafood roller. So the leaf thickness automatically more than the seafood roller, and it is 250 mm, and the number of passes is required to 3 to 5. And for fine grain fields or for rubber tire roller also used in fine grain fields or well graded coarse grain with fields more than 8%, and the leaf thickness is 150 to 200, and number of passes is equal to 4 to 6. The smooth wheel roller, which is actually the smooth roller, the roller surface is very smooth, and the compaction energy is also very less. So it is, uh, but if we apply number of passes, more number of passes, the leaf thickness is more. So it is applicable or appropriate for subgrade or base course compaction of well graded sand gravel mixture, and also may applicable or used for fine grained fields for other than the art dance. Moving ahead, there is other types of equipments like vibratory smooth drum roller, vibrating plate compactor, coil tractor, power temper roller. In vibrating smooth drum roller, it is used for coarse grain fine field sand gravel mixture etc. And the leaf thickness is 200 to 300 mm. And number of passes is equal to 4 to 6. Like the vibratory plate compactor, it is used for the coarse grain field with the less than 4 to 8% and plays thoroughly wet. And leaf thickness is 200 to 250 mm. Like then so and so. And moving ahead, now we can come to lecture 4. Now we come to the lecture 4 of the module 2. Here we solve or try to solve two problems, two or three problems in this module. First problem, it is said that the in situ moisture content of a soil at a borrow area is 14% and its moisture unit weight. That means the bulk unit weight is 17 kilonewton per meter cube. And the specific gravity of the soil solid is given is 2.7. And then the soil is excavated and transported to the construction site. This borrow pit, it is a borrow pit. Borrow pit, the soil is excavated and transported to the construction site and compacted the field. And the compacted volume is 2000 meter cube. And the compact specification of the compacted soil is given that the dry unit weight is 18 kilonewton per meter cube and at a moisture content of 16%, and unit weight of the water is given in 920. Here it is asked that what is the void ratio in the compacted soil. Second question is that what is the degree of saturation of the soil after compaction. Third one is that what is the volume of the soil in cubic meter to be borrowed from the borrow site. Fourth one is if a drum truck can carry 150 kilonewton of soil in a trip, what will be the number of trips required to transport the soil to the construction site? Fifth is what is the amount of water to be added to the borrow soil to give the desired compaction? So now we can solve this problem. In the first, in the first, it is it is uh, required or it is try to ask that what is the void ratio of the compression. For this, now we come to the solution part. For this, we can retain here the given, what are the given for borrow area, what are the given for the field area, and what are extra given. to solve the problem. To solve the first question, or Roman one, we know that the dry density is equal, that is gamma d is equal to the Gs gamma W by 1 plus E. That means Gs here, it is Gs is specific GS is specific gravity of the soil. Uh, Here it is given 2.7 gamma W is a unit weight of water in kg per meter, kilonewton per meter, that is 9.81 kilonewton per meter cube, and we have to find the E. Here it is, we written is EC. It is a suffix C is denoted the void for compacted field. And if we rearrange the formula, we can find here an formula and put all the values in this formula. We can easily find the void ratio of compacted field. Here it is, we can find that 0.47 for that problem. For solve the second problem, that is, we find out the saturation, degree of saturation for that compacted field. We can apply the formula, that is SE is equal to omega G. That is, S here, S is degree of saturation in degree of saturation in point, and E is void ratio, omega is water content of the compression field, and G is the specific weight of the specific gravity of the soil, which is also constant for that type of soil. It is 2.7. Water content is 0.16 and void ratio is 0.47, which is previously defined or we calculated. By applying or putting all the values, we can easily find that the degree of saturation is 92% or 0.92%. If you convert this percentage, it is 92%. Now to try to solve the third one, that is, we find out the volume of the what is the volume of the bore pit, from where we get the compacted volume. For that, we find out the bulk density. Find out the for that, we can first find out the bulk density of the compacted field. Then find out the from that bulk density, we find out the void ratio of the compacted field. So wait, so sorry. To solve this third one, we can first find out the void ratio of the compacted bore field. To find out the void ratio of the compacted field, we apply or rearrange the formula gamma bulk is equal to the gamma d into 1 plus omega. If we replace the gamma d, which is dye density, gs gamma w by 1 plus c, and rearrange the formula, we can easily find out the void ratio of the bore pit. After finding the void ratio of the bore pit, we can here, after finding the void ratio of the bore pit, we can find out the total volume of the, or sorry, we can find the volume of solid. For to solve this problem, we one assumption is required. That is, we know that for a particular soil volume, for a particular soil, volume of soil solid is constant. That means the volume of soil solid for bore pit is equal to the volume of soil solid of the compacted field. By this assumption, we can try to solve this problem, and we by this the volume of compacted total volume of the compacted field is given 2000 meter cube, and we also find out the volume of void ratio of the compacted field, and by B is equal to Vs plus 1 plus E formula, we can easily find out the volume of soil solid. After finding the volume of soil solid, we can find out the total volume of the bore pit. Again, same formula you use, where V is equal to total volume is equal to Vs plus into 1 plus C. Here E is equal to, we find out for Boropit is 0.77, and have also find out the Vs, it is nothing but the 1360, and put all the value, we can find easily the volume of the Boropit, which is 2416, that is 2416 meter cube. To solve the fourth one, we need to, that is number of trips, what are the, that is find out the number of trips for a track required for a track if the track carry 150 kilonewton of soil for each trip. To solve this problem, we first calculate the total weight of the borrow pit, the total weight of the soil in the borrow pit to which is compacted. To solve that, sorry, to solve that, uh, which is applies the simple formula, this volume into density, we can find the volume into unit weight, we can find the weight of the soil, and we find that it is 41072 kilonewton, and we simply divided that total volume of the total weight of the borrow pit by the weight of the per tip of a track, that is nothing but 150. We can easily find out the number of trips, and it is 200 70 200 almost 274 number of trips. Then to solve the last one, that is question 5, Roman 5 of that problem, what that is said, what are the amount to be added to the borrow soil to give the desired compaction. That means first the moisture content is borrow pit is 14%, and we achieve up to 16% to get the dry density or compacted field. To get from 14 to 16%, what amount of water is added in kilonewton is we can find out. For to find out that, we apply the simple uh, water content formula, that is weight of water by weight of solid. So first we try to find out the weight of soil solid, which is also constant for a particular site. Okay, because for a particular site, the weight of solid is not same. Particle mass is not reducing. Only void of that between the soil is reducing. So the weight of solid soil solid is always constant. So how it is find out? It is find out by the simple formula, that is Vs into Gs into gamma W. So if you put all the values, which is also some Vs is previously find out, and rest of two is also given in the question, we can easily find out that 36022 kilonewton is our weight of soil solid. Now we can find out the weight of compacted field. And for finding out the weight of compacted field, we also find out the total bulk density of that compacted field. To find out the bulk density of the compacted field, we use rearrange the density formula, and we write that bulk density is equal to dye density into 1 plus omega. Omega is nothing but the water content. Then we find the bulk density. After getting the bulk density, if we into multiply with the volume of the compacted field, we get the total weight of the compacted field. Uh, and also, if we reduce and we subtract that total weight of the compaction field from, if you subtract the total weight of the soil solid from the total weight of the compacted field, we can easily find out the total weight of the water for that compacted field. And now in case of borrow weight, we can previously we find out the total weight of the compacted field. So in this total weight of the we easily find out the total weight of the borrow pit, the borrow area, and from the borrow area, if you subtract the total weight of the solid, we can easily find the total weight of water in the borrow pit. Now, if we find out the what water is to be added, water amount of the water is to be added, we can easily subtract the total water in the compacted field minus the total water in the borrow field, and we is equal to easily find out that, which is nothing but the 688 688 kilonewton. In the unit is kilometer November. If it is solved to liter, we can convert the unit in liter. If you want it is mass or kg, it is into unit also converted into kg. So now in second question, it is very simple. It is in second question. It is uh, solved that plot the compaction curve. It is told that try to plot the compaction curve. All the values are given at different water content, different weight of the sample is given, so we can and uh, question is given that the following data refer to a light compression test is given. There's water content and weight of the sample is given for different water content, and if also given the specific gravity of the soil, which is 2.7. First question is Roman one is given that plot the compaction curve. So for that, plot the compression curve. Compression means where is left side is dry density and bottom is water content or moisture content. To plot this, we find first of all we find out the dry density. To find out the dry density, we consider the volume of the soil is or sampler is. We know that for it is written here is light compaction test. So for light compaction test, we know that the volume of the sampler is volume of the machine or whatever it is 1000 cc. So we know the weight of the uh, sample. We also know the volume of the sample. By dividing weight by volume, we get the bulk unit volume. After we getting the bulk density, and also we know the moisture content by applying the dye density formula. By applying the dye density, that is gamma d is equal to gamma bulk by 1 plus omega, we easily find out the dye density for each of the moisture content or water content, and then we try to graph sheet, we try to plot, and we can like that similar type of graph we can find out. In second question, it is told that try to plot when the degree of saturation is 80% and also when the degree of saturation is 100%. So for that we apply or modify our formula or didactic formula like that. How it is came? It is came with simple gamma d is equal to G into gamma W divided by 1 plus C. Again, we know that E is S E is equal to omega W, and if we write the E is equal to rearrange the formula, E is equal to omega W by omega G by S. We find S and replace this E here. We find out the this formula. So for 80%, that is 0.8 degree of saturation, we apply this formula, and here it is apply zero point 0.8, and we know the GS, that is 2.7. We also know the gamma W is 9.81, and for this formula we find out the different find out the different different dye density for saturation 80% for different types of water content. Again, similar for 100% saturation, similar formula is used. Here for S is equal to 1, is we replace S is equal to 1, and apply. After that, all the values is put and getting one after another, and we try to solve that and plot the graph like that. So now we try to solve in quick the previous year, or we try to see the previous year, that is 2021 assignment problems. So one by one, we quickly, actually timing is also very short. We quickly see the assignment problems one by one. First, we see that question one, we see that the roller is used to compact the coarse grain soil, which is very suitable. Now, we know that coarse grain soil is that is coarse soil is very suitable when its vibration is applied. In minimum compaction energy or compactive force, we can by applying vibration, we can easily compact the coarse grain soil, because during the application of the vibration, the particle to particle resistance reduce, particle came closer. So the suitable answer is C for that question. Then second one is told that find out the incorrect statement given below for the effect of compaction of soil. What are the incorrect? What is the incorrect statement uh, from given options? We know that for compaction of soil, we use or shallow compaction we use for increase the casting, reduce the permeability, and reduce the compressibility. So the correct here the correct option is option A, option B, D, and option C. So incorrect is increase the permeability. It is incorrect because in compaction we reduce the void space, so permeability also automatically reduce. So correct here it is incorrect option. Here it is option B. So answer is option B. In question 3, it is said that in compaction test, if the compacting effort is increased, it will result. We know that if the compaction energy is increased, for we can say that it is, if like the curve is for low energy, it is like that, for high energy like that. That if you increase the compacting effort, that means from here to here we can go, then we automatically increase the dye density and also automatically reducing the optimum moisture content after increasing the compactive effort. So correct answer is option D. That is increase the maximum dye density by decreasing the and decreasing the optimum moisture content. In question 4, it is said that the performance find out the performance of compaction equipment depends upon. And what are the factors? It is depend equipments application is depend. We know that it is depends on soil type. Also, it is depends on water type, what means groundwater level, and also depends on the particle size distribution. In soil test, that means either it is oil graded soil, post graded soil, or it is silty sand, or also water type means is or where the groundwater table is very close to the surface or not. If it is close, then compaction effort is the compaction is not suitable. Or the particle size, this is coarse grain, it is particle size is large, the fine grain its particle size is less, and also for depending on particle size, the compaction equipment also changing. So the correct answer is all of the above. So answer is it is depend on all type of all option is suitable. So correct answer is all of the above. So 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 I think time is over or very close. I try to solve. Try to Now we try to solve the question 5 and 6. Here it is given that one type of similar type of question we already solved in this our lectures. So the solution I will provided that. Here it is said that find out the void ratio uh, and also find out the degree of saturation for compactor field and also find out the volume of the borosilicate. To solve this problem, I now forward the solution. Here we see that for to solve the question 5, we applied the this formula. To solve this question 6, we applied this formula. And to solve the question 7, we applied this procedure. So we get the correct answer for that. Now, sorry. Now we try to solve question 10 and 11. Here it is said that find out the applied pressure at the base of the footing and also find out the effective overburden pressure. So to find out this problem or solution, where we see that apply this type of formula, and for find 11 we apply this formula. Okay, this no worry, these all the materials will be shared to you and in few days, and also the record session is also recorded, so nothing to worry, or everything the recording also being shared to you, so don't worry. I think the time is over now. Any if you have any doubt or any discussion, any other discussion, you can to ask me. If not, I closing the session. Hope we will meet in next session very well. It is also we will meet at next Saturday, the same time, and by that time you can go through that whatever I am taught you. We can go through that. The materials will be shared to you. You try to understand the concept and try to solve these problems, and also try to solve the previous year assignment problems, and and if you have any doubt, you can tell me now and also tell me in the next session. So I think there is no doubt regarding this session. I am trying to close this session. The here is already 8 now. So we close this session and wish you a very happy weekend for that. Good night. See you soon. I am closing now.